Alright, sorry about the delay in getting this video out, but let's go ahead here. So when we talk about formula weights are the sum of the atoms' weights for the atoms in the formula. You've calculated them before, so we just take the different, and when we talk about formula weights, we're talking about the weight of an individual ionic compound. So not its mass in grams, but masses in AMUs. So that's what like formula weight would be based on. So like calcium chloride here, mass of one calcium atom is 40.1 AMUs, and two chlorine atoms is 35.5 AMUs. And these are typically done for ionic compounds. When we get to molecular weight, so this is when we're talking about molecular or molecules, things that are bonded covalently rather than ionically. So molecular weight is the sum of the atomic weights of the atoms in a molecule. So our example being ethane here, so the mass of 2 carbons, 6 hydrogens is 30 AMUs. And you can find, and then another way that a compound might be described or initially discovered or determined is through percent composition. There's a variety of analytical tools and tests that you can do that would just give like percent composition of something. And so you get like, oh, there's a certain percentage of carbon, certain percentage of hydrogen, certain percentage of oxygen, and then you want to determine what the formula of the compound is. So we would take those percentages. So percent composition is really, the number of atoms of that compound times the atomic weight divided by the total mass of the formula weight. That would be if you wanted to determine the percent composition, but I'm going to go through how you might take percent composition to determine what the formula is. So let's say you've got percent composition of, so let's say you have 2 atoms of carbon and the total mass is 12, so this is going back to ethane, divided by the total mass, which is 30, so 24 divided by 30, so 80% of ethane, the molecule, the mass comes from carbon. Okay, we'll come back to percent composition shortly, but when we talk about mass and items, what we've talked about thus far is just individual atoms, but in reality, we have to connect it to the large scale, like how much of something we have in grams, something that we might actually utilize in the lab or those size quantities. So we have Avogadro's number to do that, to bridge the gap. And this is that connection that if we have one molecule of water, it has a formula weight or a molecular weight of 18.0 AMUs, but if we multiply that by Avogadro's number, then it's equivalent to 1 mole of water, which is 18.0 grams. So formula weight and molar weight are connected using Avogadro's number. And all of the values that are calculated on the periodic table are based on using a carbon-12 atom as the kind of the standard of what all other masses and weights are calculated from. So this idea that 1 mole of carbon-12 and only carbon-12 has an exact mass of 12 grams, and everything else is based on that standard. Okay, so molar mass, by definition, a molar mass is the mass of 1 mole of a substance, that's grams per mole. Molar mass in the element is the mass number for the element that we find on the periodic table. So you've utilized molar mass before, so this is all basic review stuff. The formula weight in AMUs will be the same number as the molar mass in grams per mole. So this is hopefully a review for you. All right, and moles is a way to go between things that we use in real world scale, so grams, and then in the molecular scale, formula units and molecules. And so we would use molar mass to convert between grams and moles. Okay, the molar mass of a compound, we would use Avogadro's number to go from moles to formula units or number of items. So that would be our conversion factor. Right, and this table just kind of gives you just kind of the concept of 1 mole of atoms, ions, or molecules contains Avogadro number of those particles. So if I have exactly 14 0.0 grams per mole of atomic nitrogen, then I will have exactly 6.02 times 10 to the 23rd nitrogen atoms, right? I mean, you got it. You can get the idea, I think. And then 1 mole of molecules or formula units contains Avogadro's number times the number of atoms or ions of each element in the compound. So the idea of barium chloride at the bottom of this table, you have a formula weight of 208.2. So that's that would be 1 atom weighs that, and then 1 mole of it would weigh the same thing but in grams. And then if you look at the number of particles, well, you would have 1 mole of the whole compound, right, of 1 mole of barium chloride. And then if you were to break it down, you would have 1 mole of barium ions and 2 moles of chlorine ions to make up the formula. All right, so how do we find empirical formulas? So this is where we use percent composition to move towards figuring out what the compound is. So this is kind of your basic setup, and we'll look at an example. But the idea is, if you know the percent compositions, you assume, well, if I had 100 grams of this sample, how many grams of each of the elements would I have? And then I slowly work towards getting mole ratios, and we'll look at that right now. So let's say I have this para-amino benzoic acid, or PABA, which is found in sunscreen, and it's composed of 61.31% carbon, 5.14% nitrogen, 5.14% hydrogen, 10.21% nitrogen, and 23.33% oxygen. And we want to find the empirical formula. So the first step is to assume that I have a 100-gram sample. So that would mean that I would have 61.31 grams of carbon and 5.14 grams of hydrogen and 10.21 grams. So, and that's the whole. So now I have, so that adds up to 100 grams. And what I'm going to do is I'm going to take those gram samples and I am going to convert them into moles by setting up the proper conversion factor using the molar mass of carbon, hydrogen, nitrogen, and oxygen. And so then I get the amount of moles that would be in this 100-gram sample of all the compounds. So now I've got moles, and what I'm going to do now is I am going to divide all of those moles by the smallest mole number. In this case, that's going to be nitrogen, since nitrogen is the smallest. So I divide them all by the smallest mole number, and then what that does for us is it takes the nitrogen value and it gives us a value of 1. And then we look at how it interacts with the other mole ratios, and you'll see that for carbon we get a number of 7, for hydrogen 7, and for oxygen 2. And it's really important that if you're going to round, so for the hydrogen and the oxygen we rounded it to 7, but if you're going to round, it has to be very close to a whole number. It can't be, so if hydrogen was 6.546, we couldn't round it to 7. We would need to leave it at 6.5. We'd need to leave it in the middle. Okay, but if it's very close to a whole number, then it's okay. But if it's right in the middle or nowhere near an edge, it's important that we don't round. And the only time that it's harder to do that is when you're doing actual laboratory work, because values tend to be not nearly as clean, and that's why it's really important to be very accurate when doing empirical formula data from percent composition, because numbers can start to look really fuzzy when you're working through that. So I take those whole number ratios and I'm now able to write the empirical formula for this compound, which is C7H7NO2. So I take all of those numbers, those ratio numbers, and I use them to then write the formula. Now, this is the empirical formula, which may or may not be the molecular formula. And to determine the molecular formula, we would need additional information to go further with that. And one way, especially with compounds that are made up of carbon, hydrogen, and oxygen, you do what's called a combustion analysis, and you basically burn the sample in the presence of oxygen, just kind of pure oxygen running through the system, and then you have a variety of chambers where you would absorb the compounds coming off. So you would determine how much carbon dioxide came off, how much water came off, and you would then be able to determine how much carbon and hydrogen was in the compound, and then after determining how much carbon and hydrogen, you could then figure out how much oxygen was also there by process of elimination. And then lastly, there are other ways to analyze compounds to determine what other compounds are in there. So, and we'll do a variety of laboratory examples throughout the course. And that's it for this. And recommendations for in class are to work on the problems, because there are quite a few today, and also to do your pre-lab for Tuesday's lab, which is the analysis of a loom lab.